Okay. Today I'm going to introduce you about introduce you to the quantum mechanics. Um, I will talk about four important concepts, very basic but very foundational important concepts in quantum mechanics. Um, they are very fundamental that you cannot miss them if you want to continue further study and if you want to know more about quantum mechanics. So the first one is the Schrodinger equation. The Schrodinger equation is very elegant, but at the same time it appears to be very difficult. But it is not the beginning of the quantum mechanics, the development of quantum mechanics, but it appeared in the midst of the development of quantum mechanics, and it just basically summarize the quantum mechanics and also give very good predictions. And the second one is the Bohr's statistical interpretation. Well, this interpretation is to interpret the solution of the Schrodinger equation. For every equation, you have a solution, and what does that solution mean is given by the Bohr's statistical interpretation. It means something about statistics and probability. And the third one is the normalization. For normalization, you is also related to probability, and it comes with the Bohr's statistical interpretation, something that force the solution to have to be normalized. And the fourth one is the measurement. What does measurement mean in quantum mechanics? What when you measure something, and it how does it related to the solution of Schrodinger equation? How does it related to wave function, and so on. So okay, so it comes with the first chapter, Schrodinger equation. Now, Schrodinger equation is written by Schrodinger, and it's very elegant, but when you look at it for the first time, it may appear to be quite complex, quite confusing. First of all, on the left hand side, you have almost some very strange symbols. What does it mean? It means for I, it means I know that you know what I means. Complex number, imaginary number. Okay, let's move on first. Then talk about it later on. And for every particle, you have you have displacement, you have acceleration, and in classical world, you describe it by the Newton's law, F equal to ma. But in quantum mechanics, when everything is in small scale, you have to describe it in something else. Newton's law fails there. So you deals with it in quantum mechanics in Schrodinger equation, and the solution of the Schrodinger equation is wave function, and it is a wave. It behaves like a wave. It depends on x and t, depends on position and time. You can see the wave function from the Schrodinger equation above. Again, the very strange symbols, and the wave function will come with the particle we want to measure, and particle comes with the wave function. So sometimes you may wonder, what does it mean about wave particle? Aren't they distinct from each other? Aren't they just distinct from each other, different from each other? And it comes with a very important concept called dualities, and it's a very complex concept. You will understand more later. So it comes again with the Schrodinger equation. We have the wave function. Again, you can see that this wave function there depends on x and t. And for v, I know I'm sure that you know what it means. It means potential, like in electricity and magnetism. It's basically and also for gravitational potential. So I'm for potential. I am like in the classical physics, something related to energy. And yeah, so let's move on to the second chapter, Born statistical interpretation. In the second chapter, Born statistical interpretation, in the past, the solution of the Schrodinger equation. In the last slide, the wave function is the Schrodinger equation solution. Solution is wave function. Wave function is solution. So maybe it's better for us to look back again to the Schrodinger equation. Schrodinger equation, on the left hand side we have the if you still remember, we have the time derivative, and on the right hand side we have we have the x derivative, which is position. Also, let us look at it again. Oh, it's very yeah, the whole solution for the Schrodinger equation wave function here. So what does it mean? Born's statistical interpretation explain it, and it's developed by Born, also a name, but the wave function is not what it was physically significant, but its absolute square is physically significant. It means probability density of finding a particle at a position at time t. But again, you can't find a particle exactly at x. You can't find a particle exactly at a precise point. So in reality, in physically, you have to give a range of position, for example, in order to measure the probability. So for example, from A to B, we have the probability from A to B, and the probability is the integral from A to B and of the probability density. Again, it's the same as you learn in high school mathematics. Probability density, something like that. For example, you have a one-dimensional line, and you have A and B, and for the line it extends from negative infinity to positive infinity. And from on this line you can find a particle, and you can find it at every point on the line. And sometimes you can find it between A and B, but sometimes you cannot. So we have to measure the probability of finding it between A and B. Again, we call from mathematics. What does it mean by probability? Probability is the number of events, number of occurrence over or between something, for something, over the number of events in the total sample space. And now the sample space is very big. It's from negative infinity to positive infinity, while the numerator is from A to B. Okay, I think Okay, now let's move on to the third chapter, to normalization. In normalization, it comes with the Bourne statistical interpretation. So normalization is about the normalizing of solution the solution to Schrodinger equation, and which is equal to again the wave function. For normalization, we want to, for example, one example will explain very well. We again have a one-dimensional line, but and also for it extends from positive infinity, it stands from negative infinity to positive infinity, and we want to find the probability between negative infinity to positive infinity. Again, from the last chapter, the Bourne statistical interpretation. Now is the A, and this becomes the B. Again, from the last chapter, we have something like this, the probability, and because it's from negative infinity to positive infinity, and in one-dimensional, you have 100% to find it there. So the probability is equal to 1, and for this thing is just what normalization is all about. For normalization, this is just all about normalization. This is the statement, and this is the concept of normalization. Now let me give you a very simple example, so that you can see. Example. For example, we have a wave function t equal to 0, at t equal to 0, but still you have varying x. Now, for example, when x is between 0 and a, you have this probability density. That's not probability density, sorry. X squared of wave function square absolute square is, but wave function itself does not mean probability density, so there's an error in my speaking. Sorry about that. It means the wave function is this, but 0 otherwise. Otherwise, yeah, sorry. Now your mission, your question is to find A, to find big A. Now you have to apply normalization concept from negative infinity to positive infinity. Just plug in here, also plug there, and now it just become something from this to there, and just here plus something else equal to 1. So now you can find the big A. Is that easy? So I'm not going to do it for you, but from normalization we can deduce something further about physics. And now I'm going to show you. For normalization, we have something integral from negative infinity to positive infinity. equal to 1. And what does it mean? It means normalization of the wave function, and this thing is the probability density, and it's denoted by F. We just recall high school math. Whenever we have probability density for F to find an expected value, for example X, we just do this. For example Y, we just do this for Y, probability density for Y. And now F is the absolute square of the wave function. Again, not the wave function, but absolute squares of the wave function, and it is F. You can deduce a lot of things from here. For example, we talk about the expected value of X, and X means the position of something, of the particle. You can write it down. You can write what X is. For example, you have X. For example, what is absolute square is something like this. Therefore, for the expected value of X,